Welcome to Hart und Trocken. My name is Dirk Schiebon, and in this video I want to walk you through a couple of examples where we translate natural language requests into SQL queries. The examples are based upon an illustrative, simple database which could be used in a web shop. This video is the second part of a series of 2 videos about this topic. Let me start by recalling the basic structure of the so-called product database we're going to work with. The name product is short for product database. The database contains 4 tables: customers, orders, products, and deliveries. The table customers contains information about the customers. The table products contains information about the products the webshop is offering. And the table orders stores information about the orders which have been placed by customers where they ordered different products or product variants. Please recall that each product comes in several variants. So for instance, the product Coca-Cola could come in the variants small, medium, and large. So in order to identify a product, we not only need the product ID, but we also need the variant of the product. Finally, there's the table deliveries, which stores for each order the time it took to deliver the order to the customer. Now suppose you are the owner of the web shop and you want to retrieve some information from your database in order to better understand your business as a basis for strategic decisions. In this video, we're going to consider altogether 5 examples of such natural language requests of the web shop owner, which we want to translate into SQL queries. In the first example, we are interested in all orders which come from customers who live in Munich. So we want to select all orders, that means all order IDs, by customers from Munich. Let's create that query in SQLite Studio. As you can see, I have loaded the product database into SQLite Studio, and you can see the tables, customers, deliveries, orders, and products. It's handy to expand these views in order to see the columns of the different tables. So we expand these all. Now we're supposed to select all orders by customers from Munich. Whenever we start to translate such a request into an SQL query, we first identify the tables from which our information come from. So in order to identify all orders by customers from Munich, we need the table orders. And we also need the table customers. I think that's about it. Let's give these 2 tables a try. So the next thing is to join these 2 tables. So orders join customers. Typically, at least in practical examples, a join is always followed by an on condition. So orders join customers on. Now the on condition needs to match rows from orders with rows from customers in a meaningful way. Obviously, in this case, we are only interested in combinations of orders and customers where the customers has been the one to place the order. So how do we create the on condition? Well, there's a customer ID in customers. And there's also a customer ID in orders. This one indicates the customer who has placed the respective order. So in the on condition, we want these 2 customer IDs to match. How do we do that? Well, we write orders.customerID should equal customers.customerID. Recall that whenever a name of an attribute is ambiguous, that means it is not unique, like customer ID, we have to additionally add the name of the table where it comes from in front of the name of the attribute. Next, let's complete that line by putting a from in front. So from orders join customers on orders.customerID equals customers.customerID. Now the next thing I usually do is to specify the select part. So what do we want to select? We're supposed to select all order IDs by customers from Munich. So we're interested in order IDs. Well, order ID. And usually I always put the name of the table where the attribute comes from in front of the attribute name for reasons of transparency. So let's type orders.orderID. So that is what we want to select. Now the next thing in the general structure of an SQL query is the where statement. So we think about if there are any restrictions regarding the datasets we want to be output. Well, yes, there is a restriction. We are only interested in those order IDs which come from customers who live in Munich. So where is the Munich? Where is the city information? Well, we have the attribute city here in customers. So we want city to equal Munich or München in German. So we type customers.city equals And now in single quotation marks, München, which is spelled with UE, München. So that should be about it. We put a semicolon in the end and execute the query. There we go. So these are the order IDs of orders by customers from Unique. Now there's one thing to point out. We see that some of these order IDs occur multiple times in the result set. These two and these two. And the reason for this is that one order can contain different products or product variants. And for each product variant, we have an extra row. Now, how could we get rid of these multiple order IDs? Well, one option is to do a group by. We group by orders.orderID. So here SQL builds groups based on the different values it finds for the order ID in the result set. And for each of these groups, only one row is output. So we should get rid of multiple order IDs. So execute this, and there you go. Now let's have a look at the second example. We want to select all products, name and variant, which were ordered by customers from Dortmund. So again, recall that a product consists of a name and a variant. So for instance, Coca-Cola in combination with small, medium or large. Now, in analogy to our first example, I want you to first think about the different tables where we need to retrieve our information from. So at first, for the product information, especially for the product name, we need the table products. Next, for the city information of the customers, we definitely need the table customers. And we also need the table orders, which contains the information about which products have been ordered by which customers. So these are three tables now, and we need to join them in a meaningful way. Well, obviously, next to one order row, we want the information of which product and variant has been ordered and which customer placed this order. Now let's build this step by step in SQLite Studio. Let's first start with a join. So we start with orders, join customers, join products. And now comes the on condition. And the on condition will consist of two parts. The first matching orders and customers, and the second matching orders and products. How can we match orders and customers? So let's have a look. In the orders table, we find the customer ID. It refers to the customers table, especially to the customer ID here in the customers table. So we need to match customer ID from orders with customer ID from customers. That means we type on orders.customer ID equals customers.customer ID. But as I said, this is only the first part of the on condition. The second is connected with an and now we need to match orders with products. So how can we match orders with products? Let's have a look in the orders table. Well, there's the product ID. And in products, there's something which is called prod ID, which is also the product ID. So we need to match product ID and prod ID. Let's do that. We say orders.product ID equals products.prod ID. Now, are we done now? The answer is no, not quite. There's something missing. The reason for this is that we said that products come with different variants. So for one prod ID, there might be different variants. For instance, for the prod ID of Coca-Cola, there will be the variant small, medium and large. This is why in the orders table, we also have the attribute variant, because variant specifies which variant of the product the customer has ordered. And that is also something we want to take account of in our join. So let's jump back to the editor window and let's add, using and, an extra condition where we also match orders.variant with products.variant. So that matching of the orders table and the products table, which I highlight here, is a nice example that sometimes we need to match more than one attribute per table in order to specify the right matching. Let me try to phrase it differently. If we didn't use this extra condition here, we might run into situations where an order of a certain customer who ordered some product in a certain variant would be followed in the join by the right product with the right product ID, but with the wrong variant. And we don't want to have that. This is why we additionally demand that the variants also coincide. Now let's continue building our query by creating the select part. So let's say select. Now what do we need to select? Well, the natural language version says select all products in brackets name and variant which were ordered by customers from Dortmund. So we're supposed to select name and variant of the product. So we select products.name along with products.variant. There we go. Now we add a from in front of orders, from orders. So next we want to take into account the restriction saying which were ordered by customers from Dortmund. So we need to restrict ourselves on datasets which come from customers from Dortmund. So we can do that by typing where. Well, now the city should be Dortmund and the city is in the customers table here, city. So we say customers.city equals Dortmund. So let's have a look what we did. The natural language version says select all products, name and variant, which were ordered by customers from Dortmund. So we select product name and products variant from this triple join with the right on condition, and we restrict ourselves to customers who come from Dortmund. Now let's execute this. So there we go. We see the name and the variant of those products which have been ordered by customers living in Dortmund. Well, maybe you have the slight feeling of how can we be sure that we did the right thing? We see that list here, but are we really sure that these products and variants have been ordered by customers from Dortmund? So one way to dive a little deeper is to replace these two attributes which we select by star. So we want to select everything, every column in that big join, orders, join customers, join products with this long on condition. So if I execute this, we get the same number of rows, but these rows are much longer, of course, because we now selected all columns in the join. And let's closely examine, for instance, the first row. So here we have an order with this ID, ordered by that customer. That product ID has been ordered in this variant, this quantity and this order date. So these columns come from the table orders. Now that is the customer. And first thing we check is that the customer ID here matches with this customer. This is the customer ID coming from the table customers. And these are the extra information which also come from the table customers. So Heinz Kwiatkowski is the guy behind that customer ID and he comes from Dortmund. So that looks good. Now that is the information which comes from the product table, and we see the product ID over here matches with this product ID which comes from the table orders. And also we have the variants matching because here the variant gold and here's the variant gold. So that looks all good. Our on condition did its job and we see in fact it's really a customer coming from Dortmund. So we are happy if our query gives us that name and that variant. And in this way we can verify the other rows as well. So that's the solution for the second example. Now the third example is the following. Select all products, name and variant, which were ordered more than 10 times. Again, we start by thinking about the tables where our information come from. Now because we need the product's name, our first table is products. And because we need the information about the ordering of this product, we obviously need the table orders. The table customers is not needed in this example. Let's start building the query by building the join. Now we're supposed to join the tables products and orders. So we write products, join orders, and now we're already familiar with the on condition. So we type on products.prod_id equals orders dot, and now here it's called product ID. And we also have to match the variants. So products.variant equals orders.variant. So next we look at the select part and we say select. Now what are we supposed to select? We're supposed to select all products, name and variant. So again, we select products.name as well as products.variant from this join. Next, we need to take into account the restriction which were ordered more than 10 times. Now, thinking of combinations of product names and variants, how can we find out how many times they were ordered? that sounds like we have to do some grouping. But by what should we group? Well, a good idea would be to group by a product name and product variant, because we want to be on the level of product's name and variant. So we don't only want to group by product name, and of course, we don't only want to group by product's variant either. So it should be the combination of name and variant. So how do we do that? We type group by, and that is something I might not have told you yet. We can group by multiple attributes. So I can group by product's name, comma, product's variant. So for all different combinations of a product's name and a product's variant, a group is created. And now within a given group of a certain product's name and a certain product's variant, we want to be sure that this exact combination of product's name and product's variant has been ordered more than 10 times. So what exactly does that mean, to have been ordered more than 10 times? Well, in the table orders, we have the attribute quantity. Quantity is a number which tells us how many times that combination of product variant and product ID, which is contained in the dataset of orders, has been ordered. So now it's important to realize that a group specified by a product's name and product's variant might refer to or might contain multiple rows in the table orders, which all contain the product ID, which belongs to the specific product name, which is the defining product name of the group, and which also contain the specific variant which has been used to define the group. For all those multiple rows in orders, which carry the same product ID and which carry the same product variant, we need to sum up the quantities and make sure that this sum is greater than 10, because they need to be ordered more than 10 times. So this is a restriction or a condition which acts on group level rather than on dataset level. Restrictions on group level are phrased using having. So we type having followed by that restriction. And what is that restriction? Well, we said we want to sum up all attributes quantity inside that group. So it's much easier to write this than to explain this. So it's having sum orders dot quantity, and that should be strictly greater than 10. And there we go. This is our query. Now let's execute this. You see all the combinations of a product name along with a product variant, which altogether have been ordered more than 10 times. If we additionally select the sum of orders quantity in the select part, like this, we can verify a little that the sum of the orders quantity is really strictly greater than 10. So execute this, and here you see the sum of the orders quantity, and you see that those numbers are all strictly greater than 10. Now let's have a look at the fourth example. We select all products, name and variant, with an average delivery time of more than 2 days. That example is very similar to the third example, except for the restricting condition in the end. So one crucial thing we discover here is that the table deliveries will have to be included, because we need information about the delivery time. Of course, also the products table is involved, as well as the orders table, which builds a bridge between the table's products and deliveries. So let's build the query. Again, we start by joining the relevant tables, which are products, join orders, join deliveries. Now again, the on condition has two parts, one matching products and orders, and one matching orders and deliveries. Now the first part, which matches products and orders, is the same as in the examples before. It consists of two parts, one referring to the product ID, one referring to the product variant. So we say products.prod_id equals orders.productID and products.variant equals orders.variant. And now we need to match the orders table with the deliveries table. You see that deliveries has an order ID in here. And you see, of course, that orders also has an order ID. So to match these two order IDs is the thing we need to do. So we type orders.orderID equals deliveries.order-id. Now again, as in the examples before, we're supposed to select the product name and variant. So we say products.name and products.variant from this long join. Now the restriction in the end says that we are only interested in those products name and products variant combinations which have an average delivery time of more than 2 days. So average is a very strong indicator towards grouping and aggregation, because we can only calculate an average if we have a group where we can aggregate over. So again, as in the example before, we group by product's name and product's variant. And the restricting condition is on group level. That means it is not where, but it is having. Now having what? If we look at the natural language version, it says with an average delivery time of more than 2 days. So where do we get the delivery time from? If we look at deliveries, we have the attribute days. So days gives us for each order the time which it took to deliver the order. So that means within all the rows of the orders table, which are defined to be a group having a specific product's name and a specific product's variant, we have to find out the days over here in the deliveries table and build the average over all these days. Well, by using the join over here with the write-on conditions, we already have these days at our disposal. So the only thing we need to do is to type average, which is avg, the function average, of, well, and now of the attribute days in the deliveries table. So we type deliveries.days. And now we know that this average delivery time should be strictly greater than 2 days. So we type strictly greater than 2. And there we go. This is our query. Let's execute it. Now again, we see different combinations of names and variants, now having the property that their average delivery time regarding all orders where they have been ordered is strictly greater than 2. Again, we can do a little verification by including this average deliveries days up here in the select area by just copying and pasting it here and executing. Now you see all these average delivery days are apparently, hopefully, strictly greater than 2. Now we look at the last example of this video. How much revenue did each product generate? And we ignore different variants. So that means, in this case, Coca-Cola is a product, and we ignore that we have small, medium or large version of it. Now, which tables do we need to retrieve our information from? How much revenue did each product generate? Well, obviously we need the table products. And what table would we join this table with? Well, obviously we need the information of how many times a product variant has been ordered in the past. So we need the table orders. So we join products with orders. And regarding the on condition, we have our standard on condition, which is products.prodID equals orders.productID and products.variant orders.variant. Well, it's important to understand that although the natural text said we should ignore different variants, we still need to match the variants here when joining the products and orders, because each product variant has a different price and we need to capture these prices. So that's why we have to have a matching also on variant level. Now in this example, the select part is quite interesting. So what do we want to select? Well, the question reads, how much revenue did each product generate? So probably we are interested in the product's name. So the first thing I wanted to select is product's name. And well, then we're interested in the revenue. Now what is revenue? Well, revenue is the money we altogether received by selling this product. So the information we need is that for any order where we sold a product variant of a given product, we need to have the information about the quantity, that means how many of these product variants have been sold, along with the price of this product variant. And the revenue for this one order is price times quantity. So for instance, if in one order we've sold 3 medium Coca-Cola, the quantity is 3 and the price is the price for 1 medium Coca-Cola. So we have to multiply price, which comes from products, so products.price, times orders.quantity. So this is the money the webshop earns for selling a specific product in a specific variant in a specific order. Now, as the question says, we're not interested in specific orders and we're not interested in specific variants either. The only thing we want to keep fixed is the product itself, which translates to the product ID. So we might want to build groups by group by based upon product IDs. Products.prod_id. So now for one specific prod ID, we want to know the complete revenue which has been generated by orders where any of the variants of this prod ID has been sold. So that means we have to aggregate these expressions. Aggregate means to sum them up. So we use the sum function and say sum of products price times orders quantity. Well, now all we need to complete this query is to add a from here in front of the join. And that's it. Let's see what happens if we execute that. And we see one column is the name of the product without any variant information. And in this column, we see the sum over products price times orders quantity, which is the complete revenue for this product. So that means, for instance, for the product named Red Apple, we have a complete revenue of 1,281.88, well, whatever currency this is in, dollars or euros. Now, as in the examples before, I don't like to leave you with the result as it is, but I rather would like to do some examinations about it. So the first thing I want to do is to leave away the group by part in order to split the groups up in single datasets again. But then the aggregation command sum doesn't make any sense anymore, so I have to take that one away as well. Okay, let's have a look at this one. So that is a rather lengthy table, and if we sort by name, which I can do by clicking on name here, you see that we have for one product many rows which all give a different revenue information. Actually, the complete revenue is given by the sum of these cells. Now, according to our way how we build the query, each one of these rows is contributed by another row from the table orders, where one variant of this product Brando has been ordered in a certain quantity. So let's examine this more closely by adding here in the select part, well, first the order ID, so orders.order_id. I'm interested from which order it comes from, and I'm also interested in the product variant, so products.variant. So you see, now we have 4 columns because we have these extra columns, order ID and variant. I think an interesting thing is to sort the result set by order ID. Let's do that. And we see we have multiple rows with the same order ID. The reason for this is that one order can contain different products and different variants of these products. So for instance, in this order, the customer ordered Buzz Cola, Mr. Fusion, Cornballer, and Mr. Fusion in these variants. Each row which belongs to this order, so this row, this row, this row, and this row, carry their own information about the quantity and the price. And this is why we need to sum up all these revenue numbers in order to get the complete revenue for this order. But that has not been the question. The question was to get the complete order for one product. So this is why I want to sort by the product name. And we'll look at, for instance, this product. You see, it has been part of different order IDs. And here it's boring because we have only one variant. But let's have a look at some more interesting. Sabor de Soledad. Ooh, so many. Can't even fit them in the window here. So maybe we look at Red Apple. So Red Apple, all these are Red Apple. You see in different variants, and they have all been part of different order IDs. Not all of those order IDs necessarily must be unique. Maybe some of them are the same. This could happen if in one order the customer ordered red apple in 2 different variants. Then for each product variant, meaning the combination of red apple and the variant, we have an extra row with the same order ID. Well, now we have reached the end of our video about the practical SQL examples. You probably have seen that it's not always perfectly easy and straightforward to build the queries from the natural language requests. For me personally, the hardest things to understand is the group by command in combination with having, and when to use them in which ways. Let me point out one last thing in this regard, which is extremely important and will prevent you from running into errors. Whenever you have a select query which uses group by, like this one, you have to make sure that in your select part of the statement, so which is this line, we have either expressions which are aggregated like sum, here, or average, minimum or maximum, or that you have attributes which have the same value throughout each entire group. Only then it is ensured that SQL selects something which we can control. Suppose, for instance, we have a group with different products name. For that group, which product's name should SQL choose? Well, it chooses one of the different products name, but we can't control which it is. And then the statement is not a well-posed statement. So you're always safe when you only select attributes up here, which occur down here in the group by statement. So for instance, if I changed that prod ID to name, we are perfectly fine with product's name. Why is that so? Well, by constructing the groups, we made sure that the value of product's name in a given group is the same for all datasets in the group, because we group by a product's name. In our situation, where I have the prod ID, that situation is not directly given just by construction. But it is ensured by the fact that we know that there can never be 2 different product names with the same product ID. So that's it for this video. Thanks for watching and see you next time.